Alright, multiple regression. Hopefully, what will happen is that if you take another stats class, this is where you would start. So this is only really a very brief beginning of multiple regression. All we've been using so far is a least squares method in order to estimate things. When we say least squares, the squares are those deviations, so the deviations between the observed and the predicted, and we're just trying to minimize those deviations. There are other methods in order to estimate models. One is actually assuming a distribution of the error term and then trying to maximize that probability. We're not doing that, but that's a different way of doing it. You don't have to do least squares. You can do something like least cubes or least quadratic, or there are other methods, but this is the most efficient one that we have for linear lines, that is. We'll talk about multiple coefficients of determination. We'll talk about some model assumptions, which are very important. And we'll talk about testing for significance, but we've already done a little bit of that. And then using the estimated regression equation for estimations of predictions. And we've done a little bit of that as well. Finally, we're going to get to categorical independent variables. This is an area that could be very useful. Alright, so multiple regression. Instead of just using one x, we're going to use multiple x's, right? Because we can be described by multiple things. At the beginning of class, I asked you to describe two students and all their different features. You couldn't really predict their behavior if you only use one of those features. You need as many of those observable features as you can get a hold of. In some cases, you have to be creative about those observable features. There are things that we can measure. We can measure height, we can measure weight, we can measure GPA, we can kind of measure IQ. Not really good at that, though. We can measure other things that have a numerical value to it. But then there are things that we can't measure. So we use categorical variables instead, which are going to be those dummy variables towards the end. These are things like gender, where you were born, what state you're in, what city you're in. Right? These are simple yes or no questions, but they don't have a numerical value in and of themselves. And if we want to somehow quantify them, we have to put them into the regression model in a way that at least squares can understand it. So the equation is still the same. We have one dependent variable and a whole bunch of independent variables. The reason we're calling them independent variables is that one of the key assumptions is that your x's are not correlated with your error term. If your x's are correlated with your error term, you get weird things happening. So that goes back to my crime and police example. If police are correlated with other things that affect crime, and they probably are, then you're going to get odd correlations, or at least odd causal interpretations. You're going to find that there's a positive correlation between crime and police. So we can't say it's causal at that point. All we can say is that there is a correlation between those two parameters. The part that we say is linear are just the betas. So we can add in additional x's that are squares or quadratics or logs of other x's that we're currently using. And in that sense, we can make the x's nonlinear. But the betas themselves have to enter in linearly. So they have to enter in just like this with plus signs in between them. But I can have a regression equation that says y1 is equal to beta 1 plus beta 1x plus beta 2x squared plus beta 3 x cubed, and so on and so forth. I can have a regression equation that does that. So it's nonlinear in the x's. My x's can be nonlinear, but the betas have to enter in linear. Now the error term has to have certain properties in order for us to say that this is an actual expected value. Now, expected value is your best guess. So far in this class, our best guess has been a mean. So think of this as a mean but along a slope, and along an actual line. For this to hold, for us to be able to get rid of that error term, we have to have the assumptions about the error holding as well. Those assumptions we talked about before was that it has the zero mean, so its mean itself is zero, meaning that any noise that we see is just random noise. 2, that its variance is constant regardless of the x's that we use. 3, those errors are independent of the x's, so there's no covariance between the x's and the error term. And then 4, for testing reasons, it's distributed normal. Because if it's distributed normal, then we can use the t-test. Otherwise, we can't do any testing. We can still estimate them, so we can still get the betas, but we can't do any testing. The notation that we use to say that we have estimates and predictions is that we always put hats over our estimates, or we use lowercase versions of the uppercase parameters. So these are the Greek letter beta, and these are just b's. You can use beta hat instead if you don't like using b's. And the estimation process goes as follows. You come up with an equation. There are a set of unknown parameters. You grab data for all those x's and those dependent variables. And then we run the regression using least squares. So the same thing we did for simple linear regression, we would do it for multiple regression. The difference here being that in multiple regression, you're essentially solving not just two equations and two unknowns, but k plus 1 equations, k plus 1 unknowns. So we try to minimize the difference between the observed value and our predicted value. The way we do that is we calculate a variance term for the difference between our observed value and our predicted value. This is the error sum of squares. And we try to make that as small as possible by picking betas that reduce that size. We already did that by hand, so we're not going to go ahead and do that the hard way. But we're going to do an example here. Programmer salary survey. Software firm collected data from a sample of 20 computer programmers. A suggestion was made that a regression analysis should be used to determine if salary was related to years of experience and the score on the firm's programming aptitude test. The years of experience, score on the aptitude test, and corresponding annual salaries for a sample of 20 programmers is shown on the next slide. Here we have years of experience, here we have their test score, and here we have their salary. All right? And we have that for 20 folks. So now we can use experience and test scores as x's and salary as their dependent variable. And more companies are doing this. And more companies are having you take essentially a mini exam. We would form our equation. We'd say that your salary is based off of a constant, years of experience, and your aptitude score plus some additional error. Because that maybe doesn't explain all of your salary. Right? There could be something else that we're missing out on. So we input the data into a computer package. Your computer package does this. It spits back out a table like you've seen before. We did it yesterday. And you get your constant, your slope for your slope for the aptitude test, and your slope for years of experience, and you're told how much of the variation that actually explains. So you see the following regression output. The constant here is 3.17, experience is 1.4, and scores is 0.25. Now, how do we interpret these? All right, now they're just numbers. How do we interpret them? To figure that out, you have to kind of go back to your data set. Your data set has salaries in thousands, all right? Your years of experience are in years, and your test scores are in points. When we go back to this interpretation, we're saying when you gain 1 year of experience, your wage goes up by 1.4. 1.4 what? $1,000. Right, so it's really $1,404. Right? An additional year of experience increases your salary by $1,404. An additional point on the aptitude test increases your salary by how much? Yeah, about $250, or $251 if we round up. Okay? Now, are these two meaningful predictors of salary? And how can you tell? So the p-value will tell you whether or not they're meaningful. Alright, so what does the p-value represent here? The p-value represents the probability that that coefficient is equal to 0. So if it's a small p-value, what is the likelihood of it being 0? Very small, all right? Meaning that it's different from 0. So small p-values tell us that those coefficients matter. Big p-values tell us that we can't distinguish it from 0. All right? So in both of these cases, it looks like those p-values are significantly small, at least at levels of alpha that we would use. So we would use 10%, 5%, and 1%. And in both cases, that's less than 1%, so these p-values would be in the rejection region. So we'd say experience and score do matter. What about the constant? The constant, it helps us make the mean of the error term 0, but we can't say it in and of itself is different from 0. Alright, so in the multiple regression analysis, we interpret each regression coefficient as follows. Beta I represents an estimate of the change in y corresponding to a 1-unit increase in xi, when all other independent variables are held constant. Now, one of the things I tried to get you to think about is saying that last part first. Holding everything else constant, so we go back here to experience, holding everything else constant, not just holding scores constant, literally everything else constant, stuff we can't see. Assuming that stays the same. Then, if we give this person an additional year of experience, their wage should go up by $1,404. Another way to think about it is you have a twin. And your twin and you are exactly the same in every way, but we're going to make one small difference. Everything else about you and the twin is the same. Right, you have the same GPA, same everything. But we're going to give one of you an extra year of experience. And we're going to leave the other one the same. How much more should you pay your twin? So that's the idea behind holding everything else constant. Again, comparing it to yesterday when I said you had a 2,000 square foot house, we add on a bedroom. It doesn't mean we actually physically add on another room. Right? It really means we put up a wall in said house. But the size of the house stays the same. How much value does a 2,000 square foot home get from moving from 3 bedrooms to 4 bedrooms? All right, so salary is expected to increase by $1,404 for each additional year of experience when the variable score of programming aptitude is held constant. Salary is expected to increase by $251 for each additional point scored on the programmer's aptitude test when the variable years of experience is held constant.